Okay, so I'm very happy to speak in this conference in honor of Sasha Veretennikov. I have many very nice memories with him. We have written several papers together, and with him I had a very special experience that I'm an author of a paper which I could not read because it's written in Russian. Okay, anyway, today I will speak on some epidemic models with varying infectivity. Okay, so sorry, I don't understand. Okay, now I see better. Oops, okay. So we consider a population of fixed size, capital N, which eventually will go to infinity, distributed in k locations, and also the number of locations will eventually go to infinity, and the locations are located for mathematical convenience on the interval 0, 1. And I have intervals. My interval 0, 1 is subdivided into intervals I and k from 1 to capital K, which is a partition of 0, 1, such that each I and k contains a point x and k, and the lengths of the intervals are all equal to 1 over k. So the important point is that individuals do not move between the locations. Okay, so there are a certain number of individuals in each location. So in location k, there are b and k individuals. So the total number is capital N, and this doesn't change over time. Okay, so in each location, individuals are either susceptible or infected or recovered. And we denote the number of individuals in those compartments at each time t at location xk as Snk of t, number of susceptible at point xk at time t, Ink of t, number of infected, Rnk of t, number of recovered. And of course, for all t, that sum is equal to b and k. Okay, so we define the piecewise constant functions of x. So Sn of tx, which is constant on the interval I and k, equal to Snk of t, and similar with In of tx, Rn of tx. Now, in each locations, there are two types of individuals. Those who are infected at time 0, and there are I and k of 0 of those who have been infected at negative times, and those who are susceptible at time t, and maybe they will get infected later, or maybe they will never get infected. So now let's lambda jk j in z minus 0 and k between 1 and capital K to be an RID collection of random elements of d over r plus. So these are random functions of time, which are IID, and they are 0 on r minus. They are 0 for t negative. Okay, and this is the infectivity of an infected individual. Okay, so here 0, the time 0 refers to the time of infection of the corresponding individual. So we think of lambda jk to be first 0 possibly during a latent period, and then it grows to a maximum and then decreases. And eta jk is the last time when lambda jk is non-zero. After that time, the individual recovers. So at time tau n jk, the individual jumps from the compartment of susceptible to the compartment of infected, and at time tau n jk plus eta jk, the individual jumps from the I to the R compartment. So as a result, an important concept in our model is the total force of infection at time t. So in classical models where the infectivity is constant, you are interested only in the number of infectious individuals. Here, we want to know at each time t what is the total force of infection at each location k. So f n k of t is the total force of infection at time t in patch k, and this is the sum of the infectivity of all the individuals who were infected at time 0 plus the infectivities at time t of those who have been infected between time 0 and time t. So an k of t is a number here. K is the subscript k is missing, is the number of those individuals in patch k who were initially susceptible and who get infected on the interval 0t. And of course, we also define fn of tx to be piecewise constant as a function of x, like the other quantities. Okay, now about the propagation of the epidemic. So pk, k between 1 and capital K being denoting mutually independent standard Poisson processes, we let ank of t be pk of integral from 0 to t of epsilon nk of s ds, where epsilon k of s is the rate of infection in patch k. So there is the one important thing is the proportion of susceptible individuals at time t in patch k times the effect of the, okay, now you see this is the force of infection at time t in patch k prime, but those infectious individuals in patch k prime can infect in patch k. Of course, so I have supposed that there is no movement, no migrations, but okay, maybe in reality, so if you like, migration of individuals may not be considered so important during an epidemic. But what happens is that during an epidemic, maybe some people move from one location to another. For instance, those who travel from one point to another for work each day, or those who go on vacation or for holidays to visit their family or to go somewhere in mountains, sea, etc. And they go there and come back. And this is, we model this not as movement, as migration, but we model this as infection at distance from one patch to another. Okay, and finally, we define the number of infected individuals at location xk and time t who have been infected for a duration less than a, and this is jnk of ta, which is those who have been infected, who were infected at time 0 and they've been infected for a duration less than a, plus those who have been infected after time 0 and who are still infected. You see this is larger than t. They are not yet recovered, but also they have been infected for a duration less than a. And again, we define this as a function of x by the same kind of formula for the other quantities. Okay, so now the stochastic finite population model is like this, written not with index k, but written with the variable x. Sn of tx is as n of 0x, the initially susceptible, minus those who have been infected on the interval 0t. Now the infected individuals are those who were infected at the initial time and have not yet recovered. So tau n minus jk, which is a negative number, remember, plus eta minus jk is larger than t. So they will recover later after time t, plus those who have been infected on the interval 0t and will recover later after time t. And then, of course, the recovered individuals are those possibly they were recovered at time 0, plus those who were infected at time 0 but have recovered since before time t, and similarly for those who have been infected on the interval 0t and are recovered by time t. Okay, so now we divide xn of tx by bn of x. So this means so that for x, this is defined for s. I'm sorry, for x equals si or r. So these are proportions, local proportions of susceptible, infected, recovered in the local population, where bn of x is defined like this. And we wish to take the limit as n goes to infinity, the limit in those four quantities, those four functions of t and x, and also in z function of t, a, and x. Okay, so we assume that as n goes to infinity, kn, the number of sites, of patches, goes to infinity. We assume that the number of individuals in each patch goes to infinity as n goes to infinity. In fact, this premium goes to infinity. This is just a condition, and also that the ratio remains bounded. So the number of individuals in the various patches are of the same order. So these are only conditions on the initial conditions. Then we assume on the initial conditions that the proportion of susceptibles, of infected who have been infected less than A, and of removed, that those quantities converge to 0 in L1 of 0, 1. And moreover, we assume that beta n, okay, maybe I was a bit too fast. I should have, okay, here, this was a rate at which someone from an infected from patch K prime infects in patch K. Okay, so this is sort of the kernel, infection kernel from K prime to K. And okay, by the way, this division by K just refers to the fact that we should think of this sum as an integral on the interval 0, 1, and 1 over K is just the length of those intervals. So this is just a discretization of the integral over 0, 1. Okay, let me go back to where I was. I think I was here. So I assume that so beta n of xx prime is essentially beta n of kk prime times those indicator functions, sum over kk prime, but there is in addition this ratio. Okay, maybe I don't want to explain this technical detail. I need this ratio anyway. So assume that those converge in L1 of 0, 1 square, and okay, then the assumption on the, remember that lambda of t is a random function, so which is, there are IAD copies attached to the various individuals who get infected, and we assume that lambda of t, that random function, is bounded by a fixed constant, lambda star, which is a constant, not a random variable, almost surely for all t. We assume that lambda is at most a finite given number of jumps and is uniformly continuous between the jumps. And the notation here, the bar here refers to proportions, but the bar here for lambda refers to expectation. Okay, so the limiting quantities. So we want to show that our objects converge to the solution of this system of equations. So we have S bar of Tx, which is initially infected minus those who have been infected between 0 and T. So in the limit, this is just a Lebesgue integral. And now the force of infection, the sort of mean force of infection at time t point x. So this force of infection coming from those who were initially infected, plus the force of infection from those who get infected between 0 and T. And then we have those quantities, the number of the proportion of infected individuals with infection age less than A and proportion of recovered individuals. And you see, okay, and then everywhere you see this epsilon bar is just this quantity. So you see, of course, it's not a PDE. There is PDE in my title. PDE will come a bit later. At this stage, there is no PDE because there is no movement in the spatial direction. But of course, the various, so X is sort of parameter, but the equations for the various X's are coupled through this this integral here. Okay. Prime. Next, I mean, system of equations parameterized by X. And the last point is that these are not differential equations, these are integral equations, because you see here you have T minus S. So you see, you have to understand this as, this is a sort of flux of infections at time S at point X. And if you have been infected at time S, then at time T, your average, because only the average enters in this limiting equation, your average infectivity is lambda bar of T minus S. Okay. Okay, so that's it. And the idea is that our main result is that those differences go to 0 in L1 as n goes to infinity, locally uniformly in T and A, and this is in probability. And the limits are given by, okay, and one part of the result says that the system given by the set of the two first equations parameterized by X, this has a unique solution. And once we know the solution of this system, then we know the two next quantities, and so this characterizes completely a unique system of functions. Okay, and so the limits are given by as a unique solution of the above set of integral equations. So as I already pointed out, only the two first quantities are unique solution of a set of integral equations, and then once you have this, you have the other quantities, and so essentially what we have to prove is that we have to prove this. Okay, once you have this, the rest is essentially obvious, and essentially you have to write those differences Sn bar minus S bar, Fn bar minus F bar, as difference of initial quantities plus those terms plus, of course, fluctuations which are hidden. This is a martingale term. This is not a martingale because you see, you have to think that this is sort of a Poisson integral, an integral with respect to compensated Poisson random measure. But there is this lambda of T minus S, and so because of the integrand depends upon T, this has no chance to be a martingale. This will be a martingale, but not this one. So this is because our model is non-Markovian because of these and the limit, and it has memory. Because the limit has memory because this system of equation has memory. The limit has a memory, not like as ODEs or PDEs. And this is a limit of non-Markovian system, and in the non-Markovian system you have less martingales than in Markovian processes. So this is one difficulty of the work. So essentially what we have to show is that the initial quantity, okay, we assume that this goes to 0, you have to show that this goes to 0, this one and this one. And for the martingale, this is not too hard. For the martingale, it's not too hard. It's a little more tricky for this term. And once you have this, you just you need also upper. I mean, in order to show that this is globally Lipschitz, you need, of course, an upper bound on those cubes, but this is not too hard. And then you use Cornwell's lemma as usual. Okay, now I announced PDEs. Now comes the PDE. Okay, so suppose now that capital F. Okay, I forgot to say one thing. It was written somewhere in the slides, but I forgot to say it, that you see capital F, the F which appears here, FFC. F is the distribution function of the duration of the infectious period, and FC is 1 minus F. So suppose, okay, here it's not absolutely necessary for what follows, but nevertheless, I do assume that capital F is absolutely continuous with a density little f, and I define the hazard function mu of A to be the density divided by one minus being divided by the probability that the person is still infectious at time A. So assume that for each x at time 0, that quantity is absolutely continuous in A, and define little I of 0ax to be the A derivative of J bar. Then for all TA, almost every x, then the function A gives J bar of TAX is absolutely continuous, and the derivative with respect to A, I bar of TAX satisfies the following first order hyperbolic PDE, which is di bar dt plus di bar dA equals minus mu of A I bar of t, with the initial condition, which is of course given like this, and a boundary condition which involves the values at various points x. Okay, by the way, I have assumed there is some A bar here because I have assumed that initially infected individuals have a maximum age of infection. Okay, so this is our result. And moreover, we have that, of course, I mean, it's sort of obvious that minus I bar of T0A, I mean, the flux of infectious with infection H0 is just the minus derivative of S bar of Tx. And it is not too hard to show that the above PDE, I mean, we have a first order hyperbolic PDE, which can be solved by the method of characteristics. And the characteristics are obvious, they are parallel to the first diagonal. And so we have that the I bar of TAX has two different values depending upon whether A is larger than T or A is less than T. And okay, we have these two values. So this is given because this is initial condition, but this is a boundary condition at A equals 0. This is not given, but then the boundary condition, the boundary function solves. Okay, the boundary function. We have a first formula for the boundary condition function, which is this formula, which is not very explanatory, not very obvious. But one can show that the boundary function solves an integral equation. So again, we have here an integral equation. You see that this function of T0x is a function of the initial condition plus of the same function I bar of S0x, I bar of S0x prime, and this integral equation has unique solution. Once you solve this equation, you know the solution of the PDE. Okay, so this is essentially what I wanted to say. References, these are references to my work with Guodong Pang, and also some of the work is joint with Raphaël Forien. So we started In fact, we started our work on non-Markovian epidemic models, where we want to be more realistic than usual models, which assume a duration of infection which have an exponential distribution, which is not realistic, and also the fact that the infectivity is fixed. This is not realistic. So we've started that work at the beginning of 2020, just before the COVID epidemic. And the first paper appeared in 2022, but we have also a paper on the COVID epidemic in 21. This paper on varying infectivity also with Raphael Forian in 21, another paper on multi-patch, etc. And this first paper with the PDE, which I presented here, but not with the spatial parameter, which has been accepted recently by this journal, and also references to other authors. And the most important one is Kermack-McKendrick. This paper of 1927, almost 100 years ago, is very, very much quoted in the literature. But this is the first paper which introduces the concept of varying effectivity, and also the fact that the duration of the infectious period need not be exponential. However, almost all authors who quote that paper, they refer only to one particular case, which is considered in one section of the paper, which is with what they call fixed rate, where the varying effectivity is not varying, it's constant, and where the duration, the rate of, where the hazard function is constant, which means exponential distribution. So we take very seriously this very much quoted paper, and our work with Guo Dongtang and Raphael Forian consists in a way in giving rigorous, strong mathematical background for the model of Kermack-McKendrick, which was introduced a long time ago. Okay, so thank you for your attention, and happy birthday, Sasha.